Ever feel like those code breakers in movies make cracking ciphers look kind of cool? Well, get ready, because our deep dive today might just give you a little taste of that, breaking down codes, but instead of secret messages, we're tackling a chapter from a math textbook all about factorization.
Yeah, and you know what? While that might not sound as action-packed as a car chase or anything, there's a certain thrill to dissecting these complex problems and boiling them down to their core elements, kind of like those code breakers, when you think about it.
Totally. We're taking that textbook chapter, the one you probably remember or maybe tried to forget from school, and we're going to uncover those aha moments, the ones that make you appreciate the elegant logic behind all those numbers.
Exactly. We're going to see how something like factoring, which can seem, I don't know, kind of abstract at first, actually reflects how we break down all sorts of complex tasks in everyday life.
All right, so let's start with something familiar, shall we? Our trusty textbook kicks things off with good old-fashioned factoring of numbers. Everyone remembers prime numbers, right? Those numbers you can't divide by anything except the one in themselves, like 2, 3, 5, 7. You know the gang.
Right, and finding the prime factors of a number is it's like revealing its DNA. You know, our textbook uses the example of 30, which breaks down into 2 times 3 times 5. So those prime factors, they're the fundamental building blocks of the number 30.
It's like reverse engineering a cake. You're taking that delicious finished product and figuring out all the essential ingredients that had to come together to make it.
I like that. I like that analogy. And just like you can't, break down an egg into something simpler when you're baking a cake, prime numbers are like those fundamental ingredients in the world of multiplication. You can't simplify them any further. Now, where it gets really interesting is when we take this same idea and apply it to algebra.
Ah, yes, algebra, where the numbers and letters collide. This is where I used to get that deer in the headlights look back in school.
I hear you, but I assure you it's not as intimidating as it might seem at first glance. Instead of prime numbers, we're dealing with something called irreducible factors when we talk about algebraic expressions.
So irreducible is basically the algebra speak for prime, but for equations.
Exactly. I mean, we've simplified it as much as we can. We can't break it down any further without getting into, like, fractions or more complicated terms. Let's take a look at an example from the textbook, shall we? It gives us 5 by psi plus 10x.
All right, so how do we tackle that?
So we need to find what's common to both 5 by y and 10x in the same way we found those common factors of 2, 3, and 5 in the number 30.
Well, both terms have a 5 and an x in them, right?
You got it. That means 5x, that's our common factor. And here's where that distributive law comes in, but we're using it in reverse. Remember how we usually use it to multiply what's outside the parentheses by each term inside?
Yeah, I think I remember that.
We're basically unmultiplying here. We're pulling out that common factor, that 5x, and what's left over, that becomes our other factor.
So 5 by psi plus 10x, we rewrite that as 5x times y plus 2.
Exactly. We've expressed that original expression as the product of its factors, 5x and y2. And the neat part is, if you multiply those factors back together, you'll get right back to our original expression.
That's oddly satisfying, like taking a messy room and organizing it all into neat little containers. But this is just the beginning, right? Our textbook mentions a bunch of other factoring techniques, right?
Oh, absolutely. Common factors, they're a great starting point for sure.
Yeah.
But sometimes you need to get a little more creative. That's where a technique called regrouping comes in.
Regrouping, huh? Sounds intriguing. What's that all about?
It's kind of like, how should I put it? Imagine you're solving one of those jigsaw puzzles. Our textbook gives us this example, 2y, y2, is 3x plus 3. Now, at first glance, there's no single common factor that jumps out at you for all 4 of those terms, right?
Yeah, I'm not seeing anything obvious either.
That's where the regrouping magic happens. We can rearrange these terms strategically, group them in a way that reveals those hidden common factors.
So instead of searching for one thing that goes into all the terms, we're looking for smaller groups within the expression that have something in common.
Precisely. Like in this example, we can group the first 2 terms and then group the last 2 terms. Notice how 2xi and 2y, they both have a common factor of 2y, and then 3x and 3, they share a common factor of 3.
Oh, okay, now I see it. It's like we've created 2 mini factoring problems within the bigger one.
Exactly. And when we factor out those common factors from those mini groups, we get 2y times x1 plus 3 times x1. Now, what do you notice?
Wait a minute. Both of those terms have x1 in them. It's like suddenly seeing that hidden image in one of those magic eye pictures.
And there you have it. Just like that, x1 becomes our new common factor that we can factor out, leaving us with x1 times 2y3.
It's like you're trying all those different combinations on a lock, and then you finally hit the right one, and click, it opens. So satisfying.
Right. And speaking of cracking codes, our textbook also talks about these things called identities, which are like, pre-proven formulas that act as like shortcuts for factoring.
Ah, those, yeah. I remember seeing those in the textbook, yeah. It'd be things like a plus b squared equals a squared plus 2ab plus b squared. Those always seemed a little, I don't know, intimidating to me back in the day.
I get it. I mean, they can seem a bit abstract when you're first looking at them, but once you get the hang of them, they're incredibly useful. Think of them like templates, almost, or patterns that mathematicians have already figured out for us so that we can just plug in our values and bam, instant factorization.
Okay, yeah, that does sound pretty handy. Can we try one out, see one in action?
Absolutely. Let's take that first identity you mentioned, the a plus b squared 1. Our textbook gives us this example, x squared plus 8x plus 16. Now, can you see how that might fit the pattern?
Let me see. Okay, so the x squared could be our a squared, and then 16 could be our b squared, because 4 times 4 is 16, right?
You're on a roll. And if 4 is our b, then 2ab would be 2 times x times 4, which, you got it, is 8x.
Whoa, it fits perfectly. So we can use that identity and just plug in those values and factor x squared plus 8x plus 16 into x4 squared, just like that.
Exactly. We've basically worked backward from the formula to figure out the factors.
That's so much easier than trying to puzzle it out from scratch. It's like having the answer key, but you still get that little thrill of solving the puzzle.
Exactly. And there are actually a whole bunch of these identities we can use, each one designed for a specific pattern. For instance, we also have a minus b squared equals a squared minus 2ab plus b squared. Notice how this one uses subtraction instead of addition.
So it's like having different tools in your factoring toolbox. You just need to know which tool is right for the job, right?
Precisely. And as you work with more and more of these expressions, you start to recognize those patterns more easily, and you know which identity to use right away.
This is really making me realize that math has a certain, elegance to it that I don't think I fully appreciated back in my school days. It's like a puzzle, but with numbers and letters.
I like that. It's true. And like any good puzzle, the more you practice, the better you get at spotting those patterns and finding the solutions.
Okay, so what other identities should we have in our back pocket? I'm ready to expand my factoring horizons.
Right, well, there's the classic difference of squares identity. AB equals a squared b squared. This one's super useful when you've got two perfect squares being subtracted from each other.
Right, like 9x squared minus 4, because 9x squared is the same as 3x squared, and 4 is 2 squared.
Perfect example. Using that identity, we can factor that expression into 3x plus 2, 3x minus 2 in a snap.
I'm starting to feel like I could take on any factoring problem you throw at me.
We'll hold on to that feeling because we've got one more identity to add to your arsenal. This one's a bit more involved. xb equal x squared, ab xab.
Okay, yeah, that one does look a little more, I don't know, intimidating, haha. How does this one work again?
So this identity comes in handy when we're dealing with an expression that has a leading coefficient of 1 on that x squared term. Mm-hmm. The key is to find two numbers, a and b, that add up to the coefficient of our x term and also multiply to give us that constant term.
So it's like a two-part puzzle. We need to find those two magic numbers that satisfy both of those conditions.
You got it. Like, let's say we have the expression x squared plus 5x plus 6. So we need two numbers that add up to 5, and when you multiply them, they give you 6.
Okay, what do you think? 2 and 3, 2 plus 3 equals 5, and 2 times 3 equals 6.
You nailed it. So using that identity, we can now factor x squared plus 5x plus 6 into x plus 2, x plus 3.
I love how these identities can take what could be a really, tedious process and condense it into a few simple steps.
It's all about recognizing those underlying patterns and then, taking advantage of the tools that mathematicians have developed over, centuries. It's like having a secret decoder ring for the world of algebra.
Speaking of decoding, there's this really cool example in the textbook that I wanted to ask you about. It kind of combines a couple of these identities together, and it involves factoring a squared minus 2ab plus b squared minus c squared. Could we break that one down?
Of course. That example shows how we can often factor an expression in multiple steps, yeah. Sometimes you need to use more than one identity or more than one technique to fully simplify an expression.
It really is like untangling a really complicated knot. Sometimes you have to try a few different things, but eventually it all comes loose.
I like that. Yeah, it's not about there being one right way to factor. It's about having all of these different techniques in your toolkit and knowing when and how to use them.
It's funny how something like factoring, which always seemed like, I don't know, just an abstract math concept from school, actually uses the same kind of problem-solving skills we need for, like, all sorts of stuff in life.
It's true. It's all about, like you said, recognizing those patterns.
Yeah.
And then breaking down these big, complex tasks into smaller, manageable steps. And, of course, using the right tools along the way. Speaking of tools, our factoring deep dive wouldn't be complete without venturing into the world of dividing algebraic expressions, I think.
Oh, yeah. Division. You know, now that you mention it, it has been a while since we've tackled that one. But it does feel like a natural next step from everything we've been talking about.
It is. And what might surprise you is those principles we've already covered, they're going to come in handy here too. Mm-hmm. Remember, division, it's essentially the flip side of multiplication.
Yeah.
Right? So instead of like building something up, multiplying, we're going to be breaking things down, dividing. It's like when you take apart some complicated gadget to see how it works, and then you realize, maybe I shouldn't have done that. I don't know how to put it back together.
I think everyone's been there at some point, right? And just like with dividing regular numbers, we can also divide a monomial, which is that single term, like let's say 6x cubed, and we can divide that by another monomial, like 2x. Okay, so back to the basics. How does that work exactly?
Well, remember earlier when we were talking about finding the prime factors of a number, we can use a similar approach here. Like 6x cubed, we could express that as 2 times 3 times x times x times x, and then 2x, that's simply 2 times x.
Oh, I see where you're going with this. So we can cancel out those common factors from the top and the bottom, just like we do when we're simplifying a fraction.
Exactly. We can cancel out a 2 and an x, leaving us with 3 times x, or 3x squared as our answer.
That is so elegant. It's like we distilled that entire division problem down to its purest form.
Precisely. And we can actually take that principle and extend it to dividing a polynomial by a monomial. Like let's take, for example, 4y cubed plus 5y squared plus 6y, all divided by 2y. Our textbook actually gives us 2 methods to tackle this. One is separating common factors, and the other is the cancellation method.
2 methods, huh? Well, options are always good. Can we walk through both just to make sure we're on the same page?
Of course. So with the separating common factors method, we start by looking for a common factor that's in all the terms of that polynomial, which in this case is 2y. So we can rewrite the expression as 2y times 2y squared plus 5 over 2y plus 3.
And then we can see that we're essentially dividing that whole expression by 2y, so those cancel out.
Right. We're left with 2y squared plus 5 over 2y plus 3. Now, the cancellation method, it's similar, but instead of factoring out that 2y from the whole polynomial, we divide each term of the polynomial by 2y individually, canceling out common factors as we go.
So 2 slightly different paths, but they both lead us to the same result in the end.
Exactly. As you get more comfortable with these techniques, you might find you naturally gravitate towards one method or the other, depending on the specific problem you're working on.
It's really about having like different tools in your toolbox. Sometimes you need that hammer, sometimes you need the screwdriver, but it's important to know how to use them both effectively.
Right. I like that. Now, the real question is, are you ready for the, I guess you could say, the grand finale of algebraic division?
Oh, bring it on. Lay it on me. What's the challenge this time?
This time, we're dividing a polynomial by another polynomial. Our textbook has a great example for us, example 15, where it has us dividing 44 times x to the 4th minus 5x cubed minus 24x squared, all divided by 11x times x minus 8. Mm-hmm. And yeah, I know it can look a little intimidating when you first see it written out like that, but we've got this, I promise.
Okay, yeah, I'm already trying to spot those common factors, but it definitely seems a bit trickier this time around.
You're right. The key here is to start by factoring both the numerator, the top part, and the denominator, the bottom part, as much as you possibly can.
So it's like we're doing a little simplifying before we dive into the actual division itself, kind of clearing the decks.
Exactly. If we completely factor that numerator, we end up with 2 times 11 times x squared times x3 by 8. So you see, we were able to factor that expression inside the parentheses even further. And luckily for us, the denominator, that's already factored, 11x times x minus 8.
And now comes the really fun part where we get to cancel out all those common factors.
No, right? It's so satisfying. We can cancel out the 11, the x, and the beta from both the top and the bottom.
And that leaves us with 2 times x times x3, which we can simplify to just 4x times x3. See, I told you we got this.
You did, and that's the point, right? by using those same factoring techniques we've been practicing, even these really complex-looking division problems become totally doable.
This has been eye-opening, truly. I never thought I'd actually say this, but I kind of enjoyed factoring. I think my favorite part of these deep dives, though, is connecting these math concepts, which can seem kind of abstract, back to the real world.
Me too. It really is fascinating how often these mathematical principles, they kind of they mirror the way we approach all sorts of challenges in other areas of our lives.
Absolutely. I mean, I know not everyone's going around factoring polynomials every day, but those underlying thought processes, like you said, they're surprisingly relevant to so many things we do.
For sure. Like, think about those problem-solving strategies we've been using. Breaking down these complex things into smaller steps, trying to find those patterns, knowing which tool to use for the task at hand. Those are valuable skills no matter what you do.
It's so true. Whether you're a programmer writing code, a musician writing a song, heck, even if you're just someone trying to organize a really messy closet, those skills come in handy.
Exactly. And beyond even just the practical applications, there's something really beautiful, I think, about the elegance of math, the logic of it all. It's about finding that underlying order in things that might seem kind of chaotic on the surface. It's about making those connections and appreciating that power of abstract thought.
I love that. That's a great way to put it. Well, before we wrap up our factoring adventure, there was this really interesting point in our textbook in a section called Some Fun. It talks about how we all intuitively understand that 64 divided by 16 equals 4, which is the same as 4 divided by 1.
Yeah. Yeah, it seems like we're just crossing out a 6.
Yeah.
But there's a little more going on beneath the surface.
Exactly. And it's such a good example of how sometimes, our intuition about numbers, it needs a little help from, well, in this case, factorization, to really understand what's happening at a deeper level. Our textbook even gives us a little challenge, to find other examples like this, where just canceling out digits might lead you down the wrong path. It's a good reminder that even in a subject like math, where we think we know all the rules, there's always more to discover.
What a perfect note to end on, I think. That sense of wonder, right? There's always something new to find, a new connection to make, a new aha moment waiting around the corner.
It's true. So to all our listeners out there, we encourage you to keep that curiosity alive, keep exploring, keep asking those questions, and keep embracing those aha moments, because you never know what you might discover. Until next time, happy factoring, everyone.